Hi. So in this video we will discuss about Dirichlet problem. This is one of the most important problems regarding the harmonic functions. So the problem is to find a harmonic function with given boundary values. So in fact this problem has its origin in a heat conduction problem and several other problems like vibrating string problem and so on. So it tells you that if the boundary values are given to be a continuous function, then you have to find a harmonic function in the interior which matches with the given boundary values on the boundary points. So this is what Dirichlet problem says, and Poisson formula solves this problem for disk. So in the disk, if on the circle the boundary values are given to be some u, then you have the Poisson formula which will give you a harmonic function on the interior which coincides with the given function on the boundary. So for arbitrary domains, this much hard problem, and we need the notion called subharmonic functions to address this problem. Now let us consider the definition of subharmonic function. A continuous real-valued function Vz in a region omega is said to be subharmonic in omega if for any harmonic function uz in the region omega prime subset of omega, the difference v minus u satisfies maximum principle in omega prime. That means v minus u cannot have a maximum in omega prime without being a constant. So this is the definition of subharmonic function. We will see some properties immediately. Now so this should happen for every u. So taking u equal to 0, it tells you that v itself cannot have a maximum. So if v is subharmonic in a neighborhood of each point in z belongs to omega, then it is subharmonic in omega. The proof is very trivial. Now, what we see, a function is said to be subharmonic at a point z naught in omega if it is subharmonic in a neighborhood of z naught. And very easily we can see that every function is subharmonic in omega if and only if it is subharmonic at each point in omega. Okay. Now, trivially, every harmonic function is an example for a subharmonic function. We will see more examples. This lemma will help us to find more examples. If v is a function with the Laplacian delta v is greater than 0, strictly greater than 0, then v is subharmonic. So this lemma can be used to construct a lot of examples. With this condition, will give you a lot of examples for subharmonic functions. Suppose v is not, so the proof, suppose v is not subharmonic, then there exists a harmonic function such that v minus u has a maximum. Right? Suppose v minus u at z0 be the maximum of v minus u. Now you compute the second derivative, then this is less than or equal to 0 because delta v, this is less than or equal to 0 and this is less than or equal to 0 at z0 because of that is from calculus, at the point of maximum, you consider the function v minus u at fix x0 and treat it as a function of y, and fix y0 and treat it as a function of x. Then these two quantities will be less than or equal to 0. So the second derivative will be less than or equal to 0 at a point of maximum. Now you compute the Laplacian delta v, that is delta v minus u, so that is also less than or equal to 0 at z0. So, but we assumed that delta v greater than 0, so this is a contradiction which this gives you the proof. Later we will show that the converse is also true provided v is a continuous function with second order partial derivative exists and continuous. Then v is subharmonic if and only if delta v greater than or equal to 0. In fact, for becoming a subharmonic function, we need not have partial derivative exists. So that we will see. Now another very important theorem: a continuous function Vz is subharmonic in omega if and only if it satisfies the inequality v of z0 is less than or equal to 1 by 2 pi integral 0 to 2 pi v of z0 plus r e raised to theta d theta. You can see that this is an inequality version of mean value property. In mean value property, that means for harmonic functions, we have equality here. So if we had equality, it was a harmonic function. That's what we have seen. In the last video, we have seen that a harmonic function is characterized by the fact that it enjoys mean value property. So subharmonic function, it enjoys inequality here. Okay. Now suppose this is a characterization of subharmonic function. So as mean value property is a characterization of harmonic function, this inequality is a characterization of subharmonic function. Suppose one is true, we are going to prove that it is subharmonic. Then for every v minus u also this is true when u is harmonic, because for u you have equality, v have inequality, so v minus u have this inequality. So since this is satisfied, you can easily see that v minus u satisfies the maximum, mean value property will give you that v minus u at z0 is less than or equal to this point. Therefore, v minus u will not have any maximum in omega without being a constant, because maximum principle follows from this mean value property. Even this inequality will give you the same proof will give you, because you have inequality here. So that tells you that the condition 1 implies that v is subharmonic. Conversely, you assume that v is subharmonic in omega, and we consider the Poisson integral pvz. So there is some problem. So this is the definition. So this is the definition for pvz. In fact, I have given it in detail here. Yeah, this is the definition. pvz is equal to, the Poisson integral with v as the boundary values. It is r square minus mod z. It is z actually. Z minus z0 square divided by absolute value of r e raised to theta minus z plus z square. So now we have pvz here. Now then pvz is harmonic, that is a Poisson integral, that is harmonic. Since v is continuous on the circle, z minus z0 equal to r, the boundary values are continuous, therefore pvz is harmonic. Now v minus pvz can have no maximum in the disk because v is subharmonic unless it is being a constant. Now recall Shor's theorem. Shor's theorem tells you that pvz converges to vz as z tends to the boundary. So v minus pvz tends to 0 as z tends to the boundary. Now consider the maximum of v minus pvz in the compact set, the closed disk of radius r. So if the maximum is positive, then it should be attained at an interior point, because at the point on the boundary it goes to 0. Therefore, since v minus p has no maximum in the interior, this is a contradiction. Therefore, the maximum of v minus pv should be 0, and therefore v minus pvz, the maximum is 0 means v minus pvz should be less than or equal to 0. Okay. In particular, vz0 minus vz0 must be less than or equal to pv at z0, and pv at z0 you will obtain, if you substitute it for z0, you will obtain to be this. So this is the inequality which we needed. Hence the proof. Now what we are going to see some properties of subharmonic function. Some of them are very trivial. If v is subharmonic, then any positive scalar multiplied by v is again subharmonic. That is easy. Then v1, v2 subharmonic, their sum is also subharmonic. That follows from this previous theorem itself, the inequality, you can apply that. Now v1 and v2 are subharmonic. The maximum of v1, v2 is also subharmonic. That requires an explanation. So suppose v is the maximum of v1, v2. So suppose v minus u has a maximum where u is a harmonic function at some z0 belongs to omega prime. Then v z0 equal to maximum of v1 z0 comma v2 z0. Without loss of generality, let us assume that v z0 equal to v1 z0. Then v1 z minus uz less than or equal to vz minus uz, because v is the maximum, so v1 less than or equal to v. This is less than or equal to vz0 minus uz0 because it is a maximum of this. So which is equal to v1 z0 minus u z0 for all z belongs to omega prime. So that means v1 minus u has a maximum. Since v1 is subharmonic, this maximum exists means it should be a constant. So v1 minus u is a constant. And this inequality will tell you that if v1 minus u is a constant, so left and right are v1 minus u, so the whatever in between them, they should be constant. So v minus u should be a constant. So that is a proof. Now, hence we proved that if v minus u has a maximum, then it is a constant, and therefore it is subharmonic. Now v is subharmonic in omega, and delta is a closed disk inside omega. Then v prime, you define v prime as pv inside delta, the Poisson integral with boundary values v, and v outside delta. Then this is subharmonic. This is a very important property. This is something we will use later. So by Shor's theorem, pv tends to v as z tends to the boundary. So therefore v prime is continuous, And by the theorem we just now proved, V less than or equal to PV in delta. So, I mean, just before we proved that. Now V less than or equal to V prime on omega, that is true because V less than or equal to PV, and the value of V prime is either PV or V. In the interior and exterior of V prime is subharmonic, because in the interior V prime coincides with PV and in the exterior V prime coincides with V, both subharmonic, so V prime is subharmonic in the interior. So we need to look at the points on the circumferences. So let's Z naught is a point on the circumference of the delta. Since V less than or equal to V prime, V minus U less than or equal to V prime minus U, and this maximum is also will lead to a maximum of V minus U. So if V prime minus U has a maximum at the point Z naught, then V minus U will also have a maximum, and therefore V minus U will be a constant. So therefore you can apply this inequality, V minus U less than or equal to V prime. This inequality will tell you that V prime minus U is a constant, and hence a proof. Now I discuss some problems here which I will discuss later. Now we come to the major problem, solution of the Dirichlet problem. Given this preliminaries, we discuss about the solution of the Dirichlet problem. Let omega be a bounded domain with a boundary gamma, f theta be a real valued function defined on gamma, and mod f theta less than or equal to m on the boundary. Now consider this collection of functions b of f corresponding to f, which are all subharmonic functions in omega, such that this left limit is bounded by f theta. So what do you mean by this? Exactly, for every epsilon greater than 0 and theta belongs to the boundary, there is a neighborhood around theta, say delta, such that Vz will be less than f theta plus epsilon whenever in that neighborhood, the z is in that neighborhood intersection omega. So that is the condition. I mean, just like the left limit or something coming to the boundary from the interior, then this inequality should happen. So first of all, Bf is non-empty because any constant less than minus m will be here. That is easy. Now this lemma is a crucial one. You define U to be the supremum of Vz with V varying over Bf. For each set, V is real valued and the collection is non-empty, so this supremum exists. So you say that it is, and also it is bounded, so therefore supremum is a finite number. So my claim is that this is a harmonic function. So the proof is very easy. So how do you prove this? Yeah. So first of all, you start from, you claim that V less than or equal to m in omega for all V belongs to Bf. For that, you consider, for a given epsilon greater than 0, you consider E epsilon, the set of all points in omega such that Vz greater than or equal to m plus epsilon. So then we see that E epsilon is a closed set. That is easy because the complement of E epsilon, so E epsilon is a subset of omega, right? The complement may contain points from omega closure complement, I mean the exterior of omega, or the boundary points of omega, or the points in omega which contradicts this. That means Vz should be less than m plus epsilon. Now this is exterior, so any point is an interior point there, so no problem about this. This is an open set. Now you take a point in the boundary. So in the boundary, since V belongs to Bf, you can apply that there is a neighborhood such that Vz less than f theta plus epsilon for all s, which is less than m plus epsilon for all z in this delta. So what happens that in a neighborhood also this inequality is satisfied. So delta is fully contained in E epsilon complement. So what happens that if it is a boundary point, then also it's an interior point. Similarly, you can prove that any point here is also an interior point of the complement of E epsilon. Therefore, E epsilon complement is open. Therefore, E epsilon is closed. Also, it is bounded. So E epsilon is a compact subset of C. So now, if E epsilon is empty, what happens on a compact set? Every continuous function has a maximum. So V has a maximum and minimum. So suppose V z naught is a maximum, that is Vz less than or equal to Vz naught for all z belongs to E epsilon. So then what happens? M plus epsilon less than or equal to Vz, less than or equal to Vz naught for all z belongs to E epsilon. So this is by definition of E epsilon, and this is because Vz naught is maximum. For all other z belongs to omega, we take a z belongs to omega, Vz is less than M plus epsilon, which is less than or equal to Vz naught from here. So therefore Vz naught is a maximum on omega also, not merely on E epsilon, it's a maximum on omega also. So therefore, since V is subharmonic, this cannot happen because we cannot have a maximum inside omega. Therefore, E epsilon cannot be non-empty, so it is empty. So E epsilon is empty for all epsilon greater than 0. That means Vz should be less than M plus epsilon for all epsilon greater than 0. Therefore, Vz is less than or equal to M. So this is what our first claim, we proved that. Now we consider a disk delta such that delta closure is fully contained in omega. Let Z0 belongs to delta. U Z0 is supremum of V Z0 with V belongs to Bf, because U is defined like that. Therefore, there exists a sequence Vn which such that Vn Z0 converges to U Z0. So Vn in Bf such that U Z0 is the limit of Vn Z0. Now capital Vn is the maximum of V1, V2 up to Vn. Then Vn, capital Vn less than or equal to Vn plus 1, etc. It's an increasing sequence, and Vn belongs to Bf. Since Vn is subharmonic, as we noticed earlier, limit z tends to theta Vnz is equal to limit tends to the maximum, but each of them is bounded by f theta for all theta belongs to the boundary. Therefore, we consider, we know this, and this will tell you that capital Vn is in Bf. So it is in Bf as well as it is an increasing, non-decreasing sequence. Now consider Vn prime, which is Vn set in outside delta, and which is the Poisson integral with the Vn boundary points at the points in delta. So Vn prime is also in Bf with property 4 we proved. So that's the property 4 we proved for subharmonic functions. So Vn prime is also in Bf. And also Vn prime forms an increasing, non-decreasing sequence. And Vn Z0 less than or equal to Vn Z0, capital Vn Z0, which is less than or equal to Vn prime Z0, which is less than or equal to U Z0. So this is from there. So now what happens? Limit Vn prime Z0 is equal to U Z0 from this, because this limit is U Z0. So by Harnack's principle, so note that Harnack's principle is applicable to the sequence Vn prime inside delta, because inside delta it coincides with the harmonic function Pvn. So Harnack's principle is applicable. So it converts to a harmonic limit, say capital U in delta. So now Vn is less than or equal to small u, because it's a supremum of them. So capital Vn is less than or equal to u. So Vn prime is less than or equal to u on delta. So limit Vn prime is less than or equal to u. So limit Vn prime is a harmonic function which is capital U. So that is less than or equal to u. And capital U Z0 is equal to small u Z0, because limit is equal to u at Z0. Okay. So suppose that, so now we need to prove the other inequality. So suppose that we do the same process with another point Z1 in delta. Choose omega n belongs to Bf and do the same process. Instead, some change is that we choose omega n bar to be maximum of Vn omega n in between, and then take omega n to be the maximum of this omega, capital omega n to be the maximum of omega 1 bar, omega 2 bar, etc. omega n bar. Then we construct omega n prime in a similar way as using the Poisson integral. Then what happens? You get, in the similar process, you will get a harmonic function capital U1, such that omega n prime converges to U1. And U less than or equal to U1 less than or equal to small u. And U1 at Z1 equal to U at Z1. Okay? Because of these properties. Now U Z0 less than or equal to U1 Z0, which is less than or equal to small u Z0, which is equal to capital U Z0. So this tells you that U minus U1 at Z0 equals 0. Therefore, U minus U1 at Z will be less than or equal to 0. Okay, and therefore U minus U1 has a maximum at Z0. So this is less than or equal to 0 and this is 0 at a point. So its maximum is attained at Z0. This happens only when it is constant, and that constant is equal to 0. So U is identically equal to U1. So if you proceed in another way, you are getting the same U, and also small u Z1 is equal to capital U1 Z1, which is equal to U Z1. So on all other points also, small u coincide with capital U. So therefore, small u coincide with capital U, which is a harmonic function in the disk delta. Therefore, you obtain that u is harmonic in the disk delta, and now this can be done in any disk inside omega. Therefore, u is harmonic in omega. So now we simply go to the final discussion about the Dirichlet problem. So let me skip many of the proofs here. This is an example where Dirichlet problem has no solutions. So I have already given that example here. So now what happens, a lemma here, it tells you that Dirichlet problem has a solution in a region with boundary values given by f. Then the solution should be this uz. I mean the uz which we consider now. That means supremum of vz with v belongs to bf. So that is easy to prove. I think I will skip the proof for you. That's very easy to prove. Now onwards I will not prove anything. I mean I skip the proof here. So if a solution exists, that solution is the solution given by this uz which we just shown to be harmonic. Now there is a notion called barrier. Let omega be a region. So the existence of the solution of Dirichlet problem always depend on the geometry of the region omega. So let omega be a region z, and omega z, a harmonic function in omega, whose continuous boundary values omega theta are strictly positive, except at the point zeta naught, where it is 0. And all other boundary points it should be strictly positive. Such a function is called a barrier at the point theta naught. And the thing is that, suppose there exists a barrier at a boundary point theta naught for all of omega, and if the function f is continuous, the function f is a continuous function on the boundary, then limit z and z naught uz equal to f theta naught, where u is the function which we considered just now, which is supremum of vz with v belongs to bf. So it is a harmonic function. U is a harmonic function which we have already seen, and we have seen that at theta naught u coincide with f. Okay, so if there exists a barrier at each point zeta naught, then you have a solution for the Dirichlet problem. So this proof is also left as an exercise or a similar topic. Now finally we discuss a geometric condition under which the barrier exists. Now the question is when does the barrier exist at each point? That is, when is the Dirichlet problem is solved. So this is, you consider some boundary like this, some point like this, theta naught like this. So omega union gamma is in the upper half, open half plane, something like this, with a point theta naught which lies on the boundary line. So the condition is that it is on the line. It lies on the line, such that it is an endpoint of a line, such that all other points are outside in the exterior of omega. That's what we consider. Okay. Then you can see that you can consider omega set like this as a barrier. In general, theta naught is an endpoint of a line segment, and of all of whose points except theta naught lie in the exterior of omega, then denotes that theta 1 as the other endpoint of the line, and consider this function, square root function, which has a single valued analytic branch outside the line, and you can consider a barrier function of this form. So this is the geometric condition. That means each point should be the endpoint of a line segment which is fully, so you can consider, say, something like the disk. So every point is the endpoint of some line which is fully containing outside the exterior, outside the omega, and only that single point is on the boundary. So you can consider wz to be this and obtain. So this is the final thing. So we can see that in a disk, each boundary point is the endpoint of a line segment whose other points are exterior to the omega. This is one geometrical condition to solve Dirichlet problem. The final theorem is this: the Dirichlet problem can be solved for any region omega such that each boundary point is the endpoint of a line segment whose other points are exterior to omega. So this is the end of our discussion over Dirichlet problem and its connection with the geometry of the corresponding region.